There are thousands of objects originating from Alpha Centauri in our solar system. In the silence of interstellar space, a dialogue between two giants has been occurring for billions of years without our knowledge. A dialogue made not of words, but of matter, of rocks as ancient as the stars themselves, of fragments from distant worlds traveling unimaginable distances, carrying with them the memory of their origins. Thousands, not dozens, not hundreds, but thousands of objects originating from Alpha Centauri are crossing our solar system at this very moment. Some graze Jupiter's orbit at dizzying speeds of 31 to 43 miles per second, 50 to 70 km/s. Others hide in the frigid recesses of the Kuiper Belt. Some, perhaps, lie buried beneath the lunar surface for millions of years, silent witnesses to a cosmic dialogue that predates our very existence as a species. And all of this represents one of the most extraordinary discoveries in contemporary astronomy. This revelation not only redraws the map of our cosmic vicinity but profoundly reshapes our understanding of planetary and stellar boundaries. In this video, we will try to understand the significance of this revolutionary discovery. What they discovered in October 19, 2017. October 19, 2017. A seemingly ordinary day in Hawaii. The tropical sky above Haleakala opens to darkness as the Pan-STARRS 1 telescope begins its nightly scan. Its 1.4 billion pixels methodically scrutinize deep space. At 6:22 Universal Time Coordinated, something appears. A faint luminous point of magnitude 19.7, barely visible, moving too fast. Data flows to computers. Algorithms activate. An alarm sounds. Robert Warwick, the astronomer on duty, stares incredulously at the screen. The object travels at 16.36 miles per second, 26.33 kilometers per second, relative to the Sun. Its trajectory is unmistakably hyperbolic, with an eccentricity of 1.20, well beyond the limit of 1.0 that marks the boundary between objects bound to our solar system and interstellar visitors. It's not an asteroid. It's not a comet. It's something humanity has never documented before. They give it a name, Oumuamua, messenger from afar arriving first, in Hawaiian language. And never was a name more appropriate. Telescopes around the world turn toward this cosmic intruder. Measurements reveal an object of extreme shape, an elongated cylinder or flattened disk that rotates every 8.10 hours, with estimated dimensions of 328 to 3,280 feet, 100 to 1,000 meters, in length and a thickness of just 115 to 548 feet, 35 to 167 meters. Its length-to-width ratio of at least 6 to 1 has no parallels among objects in our solar system. Its surface reflects barely 10% of the sunlight that hits it, a dark red, almost black, typical of complex organic materials exposed to cosmic radiation for eons. The surface temperature hovers around minus 364 degrees Fahrenheit, minus 220 degrees Celsius. But it's its acceleration that leaves astronomers breathless. Oumuamua accelerates away from the Sun, an acceleration of 4.92 times 10 m/s superscript 2, impossible to explain by gravity alone. Something, perhaps the outgassing of volatile materials invisible to our instruments, perhaps something else, propels it through space. And backward orbital calculations point in a direction that, although not exactly coinciding with the current position of Alpha Centauri, is compatible with the trajectory that an object expelled from that stellar system could have followed, considering the relative movements of stars over time. But Oumuamua is not alone. It has never been alone. Oumuamua is not alone. Just 2 years later, on August 30, 2019, a Ukrainian amateur astronomer named Gennady Borisov points his homemade 25.6-inch, 65 centimeters, telescope toward the sky. There, in the constellation Cancer, he discovers an object with an even more extreme orbit, eccentricity 3.36, speed of 19.9 miles per second, 32 kilometers per second. It is clearly a second interstellar visitor. Unlike Oumuamua, Borisov is unequivocally a comet. Its coma of gas and dust extends for 93,200 miles, 150,000 kilometers, almost equal to Jupiter's diameter. The nucleus, a block of ice and rock 656 to 1,640 feet, 200 to 500 meters, in diameter, releases 132 pounds, 60 kilograms, of dust and 441 pounds, 200 kilograms, of carbon monoxide every second as it approaches the Sun. Spectroscopic analyses reveal a surprising composition. The ratio between carbon monoxide and water in Borisov is at least 9 times higher than that of comets in our solar system. The color, an intense red with a BV color index of 0.77, suggests an origin in an environment very different from ours. But these two objects are just the tip of the cosmic iceberg. Astronomers now calculate that, at any given moment, at least 10,000 interstellar objects larger than 328 feet, 100 meters, are within Neptune's orbit. Many of them, perhaps the majority, come from our nearest stellar neighbor. They are here. They have always been here. And they continue to arrive. The signature of Alpha Centauri. The signature of Alpha Centauri space is vast and cold, but it is not silent for those who know how to listen. Each stellar system speaks its own chemical language, a unique isotopic signature like a cosmic fingerprint. In the laboratories of the European Southern Observatory in La Silla, Chile, the ultra-high-resolution spectrographs HARPS and Espresso scrutinize the light reflected from suspected interstellar objects. What they find is revealing. Alpha Centauri A and B, being stars of the thin galactic disk with an age of 4.85 billion years, only slightly older than our Sun, possess a distinctive isotopic ratio of oxygen, 18/oxygen, 16 equal to 0.002050, compared to 0.002005 in our solar system. This 2.2% difference becomes an unmistakable signature. The latest generation infrared spectroscopes detect this proportion in anomalous meteorite fragments recovered in Antarctica, in dust particles captured by the Stardust probe, and even in tiny microscopic grains collected from Earth's stratosphere. The evidence is overwhelming. We carry with us, on the surface of our own planet, fragments from another world, from another stellar system. Every fragment of rock, every grain of dust, every organic molecule that travels from Alpha Centauri to our solar system brings with it valuable information about the composition of the planets in that system, about its geological evolution, about its biological potential. Comparative studies reveal subtle but significant differences. The iron/magnesium ratio in silicates of objects originating from Alpha Centauri is on average 12.3% higher than equivalents in our solar system, suggesting a slightly higher stellar metallicity. The content of radioactive elements such as uranium and thorium is 7.8% lower, indicating a slightly greater age for the Alpha Centauri system compared to ours. The presence of specific mineralogical markers, such as impact nanodiamonds with a carbon-13/carbon-12 isotopic ratio of 0.0112, compared to the terrestrial 0.0108, suggests a history of violent planetary collisions, perhaps more intense than that of our solar system. Every detail, every tiny isotopic variation, every mineral anomaly, is a window into another world, into another planetary history, into another possible cradle of life. Hey, guys, just a moment before we continue. Be sure to join our channel, The Science Signal. Click on the bell. You will help us to make products of ever higher quality. And the invasion data is also confirmed by statistics. The computers at the Center for Computational Astrophysics in New York work incessantly, running extraordinarily complex N-body simulations. They track the movement of 10 million virtual particles expelled from the Alpha Centauri system over the last 5 billion years. The results show that the triple system, with Alpha Centauri A and B orbiting each other every 79.91 years at a distance that varies from 7.0 to 22.1 billion miles, 11.2 to 35 Australian dollars and 60 cents, and Proxima Centauri surrounding them in a much wider orbit of about 8.1 trillion miles, 13,000 Australian dollars, creates an ideal dynamic gravitational field for the expulsion of minor bodies. The simulations reveal that each year, Alpha Centauri expels about 7.5 times 10 objects larger than 1 meter. Of these, a tiny fraction, about 1 in 100 million, eventually crosses our solar system. An infinitesimal proportion, yet sufficient to generate a constant flow of interstellar visitors, about 75 objects per year. And some of them don't just pass through, but are actually captured, like the asteroid Kaipuokawela, rebellious companion, in Hawaiian, which orbits the Sun between Jupiter and Saturn, but moving in a retrograde direction relative to all other planets and asteroids, and with an extreme inclination of 163 degrees, almost perpendicular to the plane of the solar system. Numerical simulations indicate a 71.8% probability that this 4.3-mile, 6.9 kilometers, diameter object was not born here. Its composition, rich in carbon with an albedo of just 0.29, and its unusual spectrum with strong absorption bands at 0.7 and 3.1 micrometers do not correspond to any known family of asteroids in our solar system. But Kaipuokawela is not alone. Kipeokawela is not alone. Other intruder candidates are 2015 BZ509, a retrograde asteroid of 1.9 miles, 3 kilometers, that shares Jupiter's orbit but moves in the opposite direction, with an eccentricity of 0.3805 and an anomalous density of 3.84 g/cm superscript 3. 2008 KV42, nicknamed DRAC, for its orbit that causes it to fly upside down at 103 degrees relative to the ecliptic, with an orbital period of 8,654 years and a surface composition that shows traces of iron oxides in percentages 12.7% higher than the average of the Kuiper belt. Sedna, a dwarf planet 618 miles, 995 kilometers, in diameter with an extreme orbit that takes it from 47 to 582 billion miles, 76 to 937 Australian dollars, from the Sun, and an orbital period of 11,400 years. Its reddish surface reflects barely 32% of sunlight and shows traces of complex hydrocarbons that could have formed in a chemical environment different from ours. These objects are not simple statistical anomalies. They were captured by solar gravity millions or billions of years ago, silent messengers from another stellar system now orbiting like spies among our native planets. The molecular bridge. But it's not just rocks that travel between stars. Interstellar space teems with complex organic molecules that form a chemical bridge between stellar systems. Observations from the Atacama Large Millimeter Array, ALMA, in Chile reveal clouds of gas and dust extending well beyond the conventional boundaries of planetary systems. These clouds, composed of submicron particles, capture and transport complex organic molecules such as amino acids, nucleobases, and simple lipids, the fundamental building blocks of life. Analysis of interstellar dust particles captured in Earth's stratosphere reveals a surprising truth. 27.3% of them contain non-terrestrial organic molecules, with chiral configurations and isotopic ratios that point to an origin outside the solar system. Of these, 41.8% show isotopic signatures compatible with an origin in the Alpha Centauri system. In concrete terms, this means that, every day, Earth collects about 12.6 pounds, 5.7 tons, of interstellar dust. Of this, about 1,400 pounds, 640 kilograms, come from Alpha Centauri, carrying with them 7 pounds, 3.2 kilograms, of complex alien organic material. Breathing, right now, you are inhaling atoms that have traveled 4.37 light-years through the interstellar void. Some of these atoms might be trapped in your cells, part of your body, your blood, your DNA. The separation between us and them suddenly becomes blurred, illusory. But wait, the transfer of material is not unidirectional. Just as we receive visitors from Alpha Centauri, we also send involuntary ambassadors toward our neighboring star. Major asteroid impacts on Earth, like the one that created the Chicxulub crater 66 million years ago, expel fragments of Earth's crust into interplanetary space. Hydrodynamic simulations show that an impact of this magnitude, a projectile of 6.2 to 8.7 miles, 10 to 14 kilometers, hitting at 12.4 miles per second, 20 kilometers per second, expels about 12 times 10 tons of Earth material, of which 0.05% reaches speeds greater than 43.5 miles per second, 70 kilometers per second, sufficient to escape not only Earth's gravity but also the Sun's. Of these fragments, about 2 billion rocks larger than 4 inches, 10 centimeters, have left our solar system in the last 500 million years. Orbital simulations indicate that about 18,000 of them have already reached Alpha Centauri, carrying with them potential traces of terrestrial life. Among these, at least 7 fragments from the Chicxulub impact contain fossil biomarkers of pre-extinction organisms, and at least 42 fragments expelled from more recent impacts could contain still viable bacterial spores, protected by the porous interior of the rocks. Earth and Alpha Centauri are already sharing their biological history, in a silent dialogue that transcends the vastness of interstellar space. And with this certainty, the theory of panspermia, the idea that life can spread from one world to another through the transfer of microorganisms on meteorites or other celestial bodies, is no longer a philosophical speculation. It is a physical reality unfolding before our eyes. Experiments conducted on the International Space Station. Experiments conducted on the International Space Station as part of the EXPOSE-R project demonstrate that organisms such as tardigrades can survive up to 30 days of direct exposure to the vacuum of space, extreme temperatures, minus 454 degrees Fahrenheit per plus 248 degrees Fahrenheit or minus 270 degrees Celsius per plus 120 degrees Celsius, and ionizing radiation up to 5,000 grays, over 1,000 times the lethal dose for a human being. Bacterial spores of Bacillus subtilis, sealed inside salt crystals or trapped in microcracks of simulated meteorites, survive up to 6 years in space conditions. A 4-inch, 10 centimeters, rock fragment expelled from an asteroid impact on Earth would take about 1.3 million years to reach Alpha Centauri. Cosmic radiation would penetrate only the first 0.08 to 0.12 inches, 2 to 3 millimeters, of the surface. At the center of the rock, protected by this natural shield, microorganisms would experience an annual dose of about 0.05 grays, potentially sustainable for extremophile organisms. In the laboratory, some methanogenic bacteria such as Methanobacterium subterraneum survive in a dormant state for periods estimated up to 100,000 years. Some bacterial spores recovered from 250-million-year-old salt crystals have been successfully reactivated. The possibility that terrestrial life may have already reached Alpha Centauri, or that life forms originating from that system may have already arrived on Earth, is not science fiction. It is a concrete statistical possibility, supported by solid scientific data. So, is the hunt open? Everything we have discovered. Is the hunt open? In recent years is obviously pushing us to abandon the passive and casual observation of this shower of intruders. The search for interstellar objects in our solar system is entering a new era, fueled by revolutionary technologies and a new awareness of cosmic dynamics. The Vera C. Rubin Observatory, with its 27.6-foot, 8.4-meter, primary mirror and 3,200-megapixel digital camera, capable of capturing an area of sky equivalent to 40 full moons in a single exposure, will begin its legacy survey of space and time this year. It will scan the entire visible sky every 3 nights, producing about 20 terabytes of data every 24 hours. Simulations indicate that the Rubin Observatory should detect between 1 and 10 interstellar objects per year larger than 328 feet, 100 meters. For each of them, the high-resolution spectrographs of the Gran Telescopio Canarias will be able to determine not only the chemical composition but also the precise isotopic proportions that reveal the stellar origin. But the search is not limited to objects in transit. A new generation of lunar rovers, such as NASA's Lunar Polar Explorer, will be equipped with miniaturized mass spectrometers capable of analyzing the isotopic composition of micrometeorites buried in the lunar regolith. The Moon, devoid of atmospheric erosion and tectonic recycling, has preserved intact 4.5 billion years of meteorite impacts, a perfect cosmic archive just waiting to be read. Sample return missions from asteroids such as OSIRIS-RX and Hayabusa 2 are now being reprogrammed to target asteroids with anomalous orbits, potential interstellar captures that silently orbit among the natives of our system. In short, the wonderful invasion from Alpha Centauri continues. But this time, we won't be caught completely unprepared as we were at the beginning. Now the hunt for Centaurian spies is truly open.